So as you can see from the title of my presentation, I'll be talking about laser material processing. And behind this term, new dimensions, I will strongly concentrate on three-dimensional laser processing activities and adding dimensions in terms of number of control parameters to perform this type of activities. So I will be dividing my presentation in two parts. In the first hour, I will give a kind of short tutorial on the experimental aspects that people need to consider in terms of ultrafast optics, nonlinear optics, plasma physics to address this type of questions. But before that, I would like to introduce you the very nice advantages you have to do material sciences using ultrafast lasers. So when I'm talking about ultrafast laser, I'm talking about what people call femtosecond laser pulses. And to introduce the nice possibility we have this very short light pulses, I like to compare 1 second to the edge of sun, which is basically the same difference you will find between 1 second and the duration of the pulses that can be produced with femtosecond lasers. So the same way, I mean, you all know flash picture to capture extremely fast events. We have with this kind of light pulses, a flash so short that you can basically picture the fastest processes in matters. So this is a first big advantage of using this type of tools. But there is also another advantage that comes from the fact that even if these pulses have extremely modest energy in it, the fact that this energy is concentrated in an extremely short pulse duration makes that you have extreme power. So I take on this example 10 millijoule inside the 50 femtosecond laser pulse. So that's basically what you can produce on a very small scale tabletop laser. So by definition, the power is energy divided by time. This is the type of power that you can deliver on the matter. So with the same laser, you can apply extreme conditions to matter, but you have also the possibility to probe the response of that matter at the same time. So that's a very strong advantage, and that's on what people rely for the very applied field of laser processing. So if we continue to discuss these extreme conditions, to these extreme conditions, materials have no choice. It has to react to these extreme conditions. So the simplest way you can show that is by focusing these very low energy pulses inside a piece of glass, the transparent materials for the light. Thanks to this extreme power, if you tightly focus this light, you can initiate at the focus extremely high order multiphoton processes and promote electrons from the valence band to the conduction band. So in that case, locally, you have the possibility to transform the transparent dielectric material in a metallic absorbing material. And that's the way you will deposit energy locally inside the material. The simplest way in an experiment you can look at this process is to simply look at the transmission of these pulses as they interact with the glass. So this is the type of curve that you will measure if you change the pulse energy. So as you can see, at low energy, transmission is equal to 100%. I mean, that's the definition of a transparent material. But as soon as you reach an intensity level so that you can initiate this highly nonlinear optics response, then you measure nonlinear absorption, and that will describe the energy deposition inside your material. So this is very analogous to maybe what you have seen in microscopy studies. When people talk about nonlinear microscopy or two-photon absorption microscopy, when you work with a short wavelength where you have 1 photon response, of course you excite the material all along the beam path. But as soon as you work with a wavelength long enough so that the only way you can excite is by multiphoton processes, you can localize the excitation or the energy deposition. So it's very analogous, with the difference that in laser processing, most of the time, we will rely on extremely high order multiphoton absorption responses. So a direct consequence of this localized energy deposition in glass or dielectric materials can be divided in 3 types of regimes. The first one, which is a molecular rearrangement of the material that will lead uniform homogeneous refractive index change, which is a regime that people exploit, for instance, to write waveguides inside materials. The second regime is a regime where the materials reorganize at the nanometer scale. So you have a material motion driven by the electric field of the light that can cause these nanostructures that can be very attractive if you want to have higher contrasted index changes for optics application. And finally, for the most extreme conditions applied in glass, you will find what people, you will enter what people call the micro-explosion regime, which is basically extreme temperature and pressure condition applied locally, creating a shock wave that will lead in the end to a void and a densified material around. So from all these regimes, basically you can access many applications. So I've been talking a little bit already about micro-optics. You can write waveguides with the first regime. You can be relevant to create optical memories. As soon as you can carve a tunnel inside the glass, you can make microfluidic systems. Obviously, 3D machining is relevant for micromechanics, but it's also the same regimes that people exploit for the very precise surgery applications. So in the end, you see that we have something relatively flexible, and that can be also very attractive when you want to combine very different functionalities on the same system and what people call lab-on-chip applications. But the comment I'd like to make at this stage is that all these nice possibilities are mostly for dielectrics, for transport materials, so dielectrics, polymers. And we will see in the second part of my presentation that it becomes progressively feasible in semiconductors, but it's a bit more challenging. So in terms of physics behind this, if we talk only about the optics part, obviously, if you want to describe such an experiment, you need to go for propagation modeling. So, of course, to solve the Maxwell equations, but the main point that you have to consider there is that we have dealing with materials that is progressively ionized during the pulse. So when you solve this propagation equation, you need to account for the bond electron contribution for the permittivity, so linear and nonlinear optics. But you have also to consider a density of free carriers that is created progressively during the pulse. So this is more plasma optics in that case. And to account for this permittivity, I will not go through the equation, but then you have to account for all the nonlinear ionization physics that are producing these carriers in time and space. A second difficulty in terms of simulation is that in most cases, if you want to describe high resolution experiments, you need to deal with extremely tightly focused beam. So highly non-partial cases that needs to treat vectorially these Maxwell equations. So in practice, this nonlinear physics and this vectorial treatment can lead to unrealistic resources to solve. So this is also an activity where there are optimizations that are needed to find the best way to simulate all these problems. So after this introduction, I will describe a little bit what I will be showing you just after. So in the first part, so the first hour, I will describe the basics of ultrafast laser material modification, mainly what are the very important parameters that people need to consider to make experiment aiming at extreme space-time localization of light inside the matter, which is the basis for 3D processing. And then I will review briefly a few applications, but mostly about micro-optics. In the second part, I will describe some research activities on which people now concentrate to try to transfer the possibility demonstrated in dielectrics to semiconductors. So I will explain how you can do it, why semiconductors are much more challenging, and the solutions that people are currently studying to solve this problem. So first part, to control extreme space-time localization of light in matter. So you imagine that to make these 3D writing applications, you need to tightly focus the light. So the best way you can focus the light is to use microscope objectives. The same microscope objectives used by people doing imaging. So then you have to consider that the goal of any objective manufacturer is to transform a plane wave in a spherical wave the best they can. The spherical wave is a wave that will give you the smallest pulse. The only limitation you have is that if you can do this ideal spherical wave, is that it will be truncated at a given angle that defines the numerical aperture. So theta, the maximum alpha angle, is equal to arc sine, the numerical aperture. That's the definition of the numerical aperture. So in practice, you understand that this truncation of the spherical wave will cause diffraction of the light. So in practice, the best focal spot that you can produce with this system is described by this function. So not a Gaussian spot, but an array function at the focus because of this diffraction pattern. So you can solve this problem with analytical solution. If you are interested, you can refer to the Born and Wolf principle of optics textbook. But of course, you can solve this problem with numerical simulation in a quite easy way. The advantage of numerical simulation is that then, when you have this type of simulation working, you can also describe non-ideal cases compared to this one, which is a pure theory case. So if we start to look at the practical cases, the first things that you have to consider and which can be different to microscopy imaging is that we will send the laser beam inside this microscope objective. And a laser beam by nature has a Gaussian profile. So in practice, it means that you will tend to put as much as possible the energy inside this objective, and you can start to introduce what we call the filling parameter, which is a ratio between the entrance pupil of your lens and the size of this Gaussian beam. So then you can understand that when beta equals to 0, it means that the Gaussian beam is extremely large. You are close to the plane wave, uniform plane wave, as I was describing just before. So then we find on this profile the array function. In practice, you can decrease the beam size to have the maximum of energy entering the lens, but then in that case, the advantage is that you can turn to Gaussian optics approximation in the sense that there is no diffraction anymore, and you have a Gaussian propagation. You find Gaussian everywhere in the beam path. The drawback is that, and it can be seen there, is that the spot size is increasing simply because you are decreasing artificially the numerical aperture of your lens by decreasing the beam size. So in practice, people are more dealing with intermediate cases. So beta equals to 1, 2, as it is calculated there, and we have to account for these aspects. Second practical aspect that people will face is the problem of spherical aberration. The problem of spherical aberration is that when you try to focus this light inside a material, there will be spherical aberrations that are caused by the refraction of light at the air-material interface. This refraction will cause that all the angular components will not focus at the same distance inside the material and will create distorted spots. So this is, for instance, the calculation for a spot in air. As soon as you put you put it 350 micron inside glass, this is what you expect from linear optics. So this is an effect that is based on the refraction on the interface. So of course, it scales with the index of the material. So if you make the same calculation in silicon, which has a refractive index of 3.5, this is what you find. So the beam is not exactly what you expect it to be. And so you have to address also this type of problems to make control machining of inside materials. So in practice, this is not something specific to laser processing. It's also something people face for imaging. So the advantage is that because it's something also important for imaging, you can find to compensate this problem objectives that are specially designed for this. Either they have a correction collar to adjust for a given thickness of material, or they are corrected. This is the number you see there for a given thickness of material. And in the end, if you operate this with the proper correction, this will be the spot you will find inside the material. So the spot size is the same in air or inside the material, but along the beam path, it's scaled with the refractive index. It's elongated, but it's a perfectly focused spot in that case. So if we simply summarize these special characteristics, I mean, I will not go through these numbers. There is ways you can simplify, estimate, validate that you are dealing with a well-controlled beam in space, but we are talking only the linear consideration. Of course, you have a spot size that is as small as the numerical aperture is high. You can also predict the elongation depending on the diffraction features. But the point I would like to emphasize now is that this is the spatial characteristics, but we have also to be aware about the temporal characteristic of the pulses when you are processing. So the main problem in terms of linear optics that you have to address is the problem of group velocity dispersion. So when you work with extremely short pulse durations, in practice, you can see the pulse as a superposition of many spectral components. I mean, that's the principle to create these extremely short pulses. So you basically lock the phase of all these frequency components so that they constructively interfere to create this short pulse. So in practice, you can write this pulse like and decompose over the spectrum this extremely short pulse, and then you can calculate what is the pulse after it propagates through a given thickness of material by simply adding a phase term there. This phase term, if you write it in terms of Taylor expansion, you will find constant, which is not doing anything in terms of pulse shape. A linear term, a linear phase shift that actually describes the delay of the pulse inside the material, but is not modifying the pulse shape. The interesting term comes now with this one, the quadratic phase shift, that describes the fact that not all angular components will propagate with the same speed inside the material. And so the red will propagate faster than the blue. And this will cause a stretching of the pulse. So in practice, you can work with extremely short pulses, extremely fast lasers, and do an experiment that is done with actually with a longer pulse. So that's something you should be aware when you do experiments. And you can even look for the shortest pulses to higher order dispersive effects that can also distort in time the pulses. So for ideal pulses, you can somehow estimate this stretching effect. So obviously, so this is, for instance, the output pulse duration for different input pulse duration as a function of the amount of GVD that describes this dispersion inside the material. So what you see there is that the shortest pulses are the most subject to this stretching, simply because to create a short pulse, you need a broad spectrum. So broader is your spectrum, more sensitive you are to these dispersion effects. And so if you take the number, is, for instance, if you take a 10 femtosecond laser pulse at 800 nanometer, and you propagate over a few meters in air or 1 millimeter in glass, it will become the pulse duration will increase by 40%. It will become 14 femtosecond, which is not negligible for an experiment. And that's something you have to account. If you take a 100 femtosecond laser pulse, you will need at least this amount of GVD to start to see an effect. But this amount of GVD is obtained if you propagate 2 or 3 centimeters of glass, which is not huge. And on an experiment, you can propagate easily through few centimeters of glass. And so you have to also to be aware of this if you want to make experiments with well-known parameters. So, but the same way you can compensate for spherical aberration, you can compensate for GVD group velocity dispersion. So, as I said, in practice, a short pulse can be seen as a superposition of many spectral components. And in practice, most materials will exhibit a positive GVD. That means that the red will propagate faster than the blue and create this short pulse when you propagate. So now, if you make a system that exhibits a negative GVD, so this is something you can fairly well control by dispersing arrangement like grating pairs, prisms, chip mirrors. Depending on the level of GVD you want, you can use different techniques. But then you understand that with this negative GVD, you transform this pulse in a stretch pulse again, but with the blue arriving before the red. And so then when this pulse will propagate with the positive GVD material, it will recompress the pulse for yourself. So that's a technique. If you prepare your pulse with negative GVD, you can deliver where you want to perform the experiment, the shortest pulse duration you can obtain with a given laser. In practice, this does not require necessarily to make a specific system to correct for this, because most of the lasers we use for laser processing are what we call amplified femtosecond lasers. So we have a femtosecond laser oscillator, but to reach enough energy level to get modification, we rely on the CPA technique. Most of the lasers we use rely on the CPA technique, which is the technology from which Gérard Mourou got recently the Nobel Prize. But it consists in the fact that to bring femtosecond laser pulse at the high energy level without damaging the amplifying medium, you need first to stretch the pulse with a grating pair. Then you can amplify this long pulse and recompress with another grating pair. So you understand that at the output of all the lasers we use, we have a grating pair that we can use to pre-compensate GVD for laser material processing experiment. So this grating pair, focusing the light inside the material, and then I return to the very simple experiment I was showing in my first slide. A photodiode, looking at the transmission of the pulse. Less transmission I find, more nonlinear absorption I have, means that my pulse becomes shorter. So if I minimize the transmission level with a simple photodiode there, moving the grating there to adjust the GVD, I can make sure that I do my experiment and perform my experiment with the shortest possible pulse. So my point there is most to say that you can, there are practical solutions to all these type of considerations, and that's the principle. That's what are facing experimentalists in ultrafast optics in many fields. So, but at this stage, I've been talking only about linear optics. So we have the spatial aspect, but we are dealing with the same problems that people will face for microscopy imaging. So if you know how to read all these labels and you know for what have been designed all these microscope objectives, you can work in a clean manner. And for the temporal aspect, if you look at the GVD that is well tabulated for most materials, you can somehow predict and pre-compensate this type of problems. But again, this is linear optics, and we have to consider that there will be in the case of laser processing, nonlinear space-time, but also spectrum distortion that will be expected because of the high intensity of the pulses we use. So then I turn to nonlinear optics, nonlinear propagation. Probably you heard already about the effect, which is highly representative of this field, filamentation. Filamentation is based on the competition between two effects. What people call the Kerr effect that describes the nonlinear refractive index. So it consists in writing that the refractive index is a constant plus a constant multiplied by the intensity. So the nonlinear refractive index multiplied by the intensity, which is obviously a function of space and time. That makes that the apparent index seen by the light, by this intense light, depends on time and space. If we look at the space problem, again, we irradiate the material with Gaussian beams. That means that the intensity is higher at the center of our beam. And beam center, higher at this beam at the center, then will experience a refractive index which is higher than the surrounding part. So the phase will be delayed at the center compared to the surrounding part. That's exactly the effect of a lens. And so that's the reason why this effect will cause what people call the self-focusing of the light. So simply by propagating this Gaussian beam, it will tend to, by itself, focus inside the material from this effect. In practice, when we do processing, we also ionize the material. And if you look at the expected index change with plasma formation, so free carrier formation, I mean, you find a negative refractive index that scales with the free carrier density. And it's obvious that the free carrier density is higher where the intensity is it's at its highest level. So the same way the intensity has a Gaussian profile, this free carrier density has also a kind of Gaussian profile. And it will create not now a positive focusing effect because of this positive term, but a defocusing effect thanks to this negative term. So in practice, intense light, as it propagates, will tend to focus and defocus by these two effects and create equilibrium conditions, causing what people call the self-trapping of intense light. That's the filamentation. So again, when it propagates, the light tends to focus, but when the light becomes sufficiently intense, it starts to ionize the materials and create a defocusing of the light. And so that will cause the trapping of light at a given intensity, at a given size. Obviously, you understand that these effects, I mean, I describe these effects for a perfect Gaussian beam. If you have an uneven beam with hotspot or whatever, this can cause a strong distortion of your beam and should be also accounted, but it's for most of the time for ultra high power laser beams. So now to finish with this consideration, I'd like to emphasize that actually all these nonlinear physics aspects actually tend to limit the intensity you can deliver inside the material. So if we look at the condition where we have this filamentation, so it consists in writing that the permittivity coming from the nonlinear index compensate the index change caused by plasma formation. So this is a nonlinear index, and this is the description of the index change with a simple Drude model that scale with the free carrier density of a plasma. If you consider that these free carriers are created by a multiphoton absorption process, multiphoton ionization process, it scales as the intensity to the power k, k being the number of photons to cross the band gap. So if you put all you put this equation inside this one, you will end with the conclusion that an intensity is defined by all these constants. So it's like the filamentation is imposing a given intensity, and it will be very hard to exceed this intensity. If you calculate this if you put the numbers for silicons, fused silica, or air, these are the intensity level you find. So the main point there is that we have lasers that can, in principle, deliver intensities much higher than these numbers. But in practice, when you will start to interact with the material, the physics will impose this intensity level. So that's also something that is very important to consider. And people talk about intensity clamping in the sense that the intensity will tend to saturate depending on materials at given numbers. So this clamping can be easily described with filamentation, but filamentation in laser processing is most of the time something we prefer to avoid. But the clamping is something general. It's not something specific to filamentation. It's something that comes from most aspects of this nonlinear physics. Now, if we consider, we do not consider the defocusing of the light by the plasma. We simply consider the energy losses by nonlinear absorption of the light for a focus beam inside the material. So I return to my first very simple experiment, transmission of light as a function of energy, 100% transmission because it's a transparent material, and then it drops because I measure nonlinear absorption. What I want to show there is how well I can describe this drop. I mean, it's not perfect, but with a very simplistic description, what I call the lawnmower modeling. So I call it lawnmower simply because the idea is that when you focus the light and you assume that all the light above a given intensity, that's the intensity threshold above which I estimate the light will start to be absorbed, I take everything. So basically, as I approach the focus, I cut the light at a given level. And if I set this number at 10 to the 13 watt per square centimeter, I mean, I can relatively well describe at least the initiation of nonlinear absorption. But it will be impossible, you understand from this experiment, but it will be impossible to deliver more than 10 to the 13 watt per square centimeter. After the focus, there is no cut anymore because the light is diverging. And everywhere in the prefocal region where I have deposited energy, I mean, I have deposited the energy with the same intensity level that leads to this very uniform excitation of the material. But again, I'm dealing with an experiment where I cannot expect to perform a modification at an intensity level more than 10, 13 watt per square centimeter, even if it was very interesting. But that's also something very specific to the bulk interaction. Now, in this case, I do not consider the losses by nonlinear absorption, but only the effect of the plasma. So I will explain a little bit after how we measure this, but what I show on this image is a snapshot of the free carriers that we create at the focus with the light. The point I would like to emphasize here is that as soon as the free carrier density will approach what we call the critical plasma density, the plasma will strongly refract the light. And so it will be very hard to deliver more energy to the region where you obtain this density. So in practice, the same way it will be hard to deliver more intensities at the 10 to the 13 watt I have shown before, it will be hard to make an experiment in the bulk with a critical plasma density that exceeds this number, because the light will start to, because the plasma will start to delocalize the light. And that's the main reason why modification inside silicon by this type of experiments have not been reported for a long time because of this limitation in standard configurations. But I will come to this in the second part of my presentation. So my very important message from this part is that it's very important to be aware that when you do an experiment in the bulk of a material with these extremely intense pulses, I mean, the local intensity is never what it could be in vacuum or at the surface of a material. And that's the main difference between bulk laser processing and surface laser processing. Obviously, you can exceed this 10 to the 13 watt per square centimeter if you interact on the surface, but in the bulk, because of this interaction physics in the bulk, you will limit the thing. In reality, any attempt to deliver more intensity in the bulk by increasing the energy level will simply degrade the resolution. Simply, you will interact with more and more material, but you will never enhance the energy density deposited inside the material by increasing the energy above a given level. So after this introduction, I move to the second part where I will briefly describe the simple applications that you can address with this type of approaches. That depends on the excitation densities, obviously. But again, on these few examples, I will concentrate on optical functionalities that can be created by laser writing. So the first example in terms of technology I would like to emphasize is two-photon lithography. I mean, same as lithography. If you repeatedly ionize a well-designed resin, you can photo-dissociate some initiator molecules that will create radicals reacting with liquid state monomers to create highly cross-linked solid state polymers. And this is the principle of 3D fabrication you can rely and the type of structures you can create. So this is more to illustrate the level of precision you can achieve. But at least from this image, you can remind that sub 100 nanometer resolution can be achieved by these technologies, and now even with commercial systems. So with this type of structures, obviously, it is very interesting to make complex photonic band gap crystals and other macro optics application, but it can be also relevant for macro machines, microfluidic and medical devices. Now, as I have introduced, I mean, this is a technology that is also widely used to create waveguides in glass materials. So if we take the example of fused silica, if you repeatedly ionize with low intensity, sufficiently intense pulses inside glass and propagate the beam, the transformation you will cause to this amorphous fused silica glass is that you will move to an organization which is called 5 to 6 member rings to 3 to 4. So that's basically you change the density of the material as you propagate, but you keep it amorphous. And you do it in a crystal. So this leads you to the possibility to be very flexible in the sense that you just need to move the beam the way you want to create what you need, but also you have extremely stable structures. So this extremely stable photonic circuits that you can create by laser writing can be associated to specific application, but they are also very attractive for quantum information science demonstrations, because then you can write very stable, the very stable interferometer you need to make these quantum science applications. And obviously, you take benefit from the flexibility to make hybrid systems or to prototype systems in an easy way. So now above this regime where you get indextions, I was saying that you can enter what we call the nanostructuring regime. So basically, in the focal volume, what you find there by repeatedly ionizing the glass, the fused silica in this case, you find these planar nanocracks across the focal volume that comes naturally, and that gets perfected as you increase the number of shots. So the main advantage of this is that this regime can cause positive indextions, typically 10 to the -3, which is ideal to create waveguides. But if you want higher refractive index, this regime can be interesting, with also the interesting aspect that most of the time you exhibit a negative index. So then you have the possibility for index engineering inside materials. So the way we can explain this negative large index change can can be done on the basis of the same way you can explain the response of some photonic crystals. So if you assume that you have made planar voids inside the glass, and each plane has a size much smaller than the wavelength, then you can assume that the field is uniform in each region. So that will be this picture. Now, if you illuminate the light with a polarization perpendicular to the planes, because you have the continuity of the displacement vector, the field which is defined as the displacement vector divided by the permittivity, you understand that the light will tend to occupy the low index material first, at the highest level. So that's the reason why when you irradiate light on this structure, it exhibits a refractive index which is lower than the glass. This is not something specific to these nanoplanes. It's something general. If you can put inside a material nano volume of low index material, it will decrease the apparent refractive index. But my point is to say that this decrease can be higher than what you can expect just by considering the volumes because of this polarization consideration. And also the important point is that the size of these features has to be, if you want to limit the scattering losses, has to be very small. So in practice, much smaller than the wavelength. But the point is that it's possible to engineer the refractive index, limiting the scattering losses by this type of approaches, basically nanostructuring glasses. In an experiment, the simplest way you can exhibit this large negative index change is simply by looking at the divergence of the beam creating the nanostructures. So this is a beam, this is a focus beam, focus inside the glass, creating the nanostructures. And this is how looks the beam after you irradiate the glass. So after you create something in the focus. So you see we have a divergence change, but we can also quite simply explained by the fact that when we modified a biconvex volume. I mean, the focal volume is biconvex by nature. So it's a microlens. And to describe this divergence change, then this is the typical number we need to put in the model. So it's an indirect evidence that by processing, we are creating an index change minus 2% in this particular experiment, which is very high, considering that we are dealing with always the same glass. The nice aspect with these nanostructures that comes in fused silica and other glassy materials is that it does not only exhibit a large index change, it also exhibits birefringence. So you probably know birefringence by a crystal birefringence that comes from the anisotropy of crystals at the molecular scale. In this case, we call it form birefringence because it comes from the anisotropy at the nanometer scale, not at the molecular scale. So again, if you consider a polarization perpendicular to the planes, I mean, you can calculate and predict what's apparent index change. But if you irradiate this structure now with a polarization parallel to the planes, now you have the continuity of the electric field. And this is what you will expect in terms of index change. So you have two index curves. So that means that with this consideration, this 2% index change we obtain actually translate in an apparent birefringence, which is also extremely large, typically 1% obtained by this transformation. So the same way you can probe the index change, you can probe the birefringence when you write the nanostructures. So in that case, we write the structures with a given polarization, and we probe with a light with polarization at 45 degrees. And then we measure the polarization state transmitted through the structures as they are produced. So what you see on this graph is that increasing the number of shots to write the structure, so the structures gets perfected shot after shot. the probe polarization moves from linear to circular. So it's more than a quarter wave plate effect obtained in a microscale volume to even more than this circular polarization. So my point there is to say that you can locally control the polarization of your light and do polarization optics with this type of writing approach. This leads me to maybe the last example I will give for micro-optics. So I show on this image the first demonstration of optical data storage by femtosecond laser writing in an experiment in the 90s, where you see that by producing or not damage locally inside the glass, you can somehow store binary information. So this experiment with up-to-date technologies now translate in this. So now the idea is that for each pixel, no need to encode binary information. We are creating these birefringent structures. So it's possible for each pixel to inscribe a given retardance level. So based on the reading limitation, people have demonstrated that they can differentiate at least 32 states of retardance level, of birefringence level, if you wish. And the orientation of the birefringence can be controlled by the writing beam. So again, based on reading limitations, they have demonstrated more than 8 states that could be readily retrieved from this. So in practice, you see that then they deal with a technology that they call 5-dimensional data storage, because they rely on the 3-dimensional space, and they add these 2 dimensions to store information. So in terms of the best demonstration, this leads to more than 360 terabytes per disk that can be written by this method. Not necessarily for to be used in a routine basis, but with the advantage that it can be done in a very stable material. It's in a glass, in a crystal, if you want. So people are envisioning this type of technologies for perennial memory technologies. So people have been looking at how stable are the nanostructures that you create in glass, and looking at how it survives to thermal treatment, so that they can make this type of Arrhenius law, from which they extrapolate that actually the lifetime of these structures is a billion of years. That is that fits the purpose of perennial memory technologies. So this is the end of my first part. I think we can maybe make the break at this level. I can also take the question even now for this first part if you wish. I don't know exactly for the timing. So maybe I can take a couple of questions.
So if I understand well, in order to read that data that is in the middle, the laser has to pass through that data that is out of focus. Does it make it harder to read?
Very good comment. I think that's probably one of the limitations you may face by this type of approaches. The point you need to consider is that all these pixels remain transparent. Yeah, I'm not sure how this will limit. Probably depends on the density of pixels you inscribe. It's true that the authors have not totally addressed this question, I think. But this 360 terabytes per disk, where demonstration was done in I would say realistic environment. So it was apparently relevant for real application.
I was wondering, probably I misunderstood something, but when you said there's a maximum threshold for the intensity inside of inside the glasses, and you said that you used a lone Mauer model. So where does like the missing energy goes? Because if you like cut off the
That-
top, yes.
A good point. This energy is the energy you use to modify the material. That's the energy that will be at some point transferred to the lattice to create the modification. That's a useful energy. But this is a good comment. We don't really care about the delivered energy. What we care is the absorbed energy. And that's the absorbed energy we describe there. So it's for sure an oversimplistic model I show with this. Huh? The point is more to say that this very strong simplification actually describes some qualitative responses we observe in the experiments. So first, we observe that the modification preferentially develops in the prefocal zone. And we can also observe that by increasing the energy, we do not change much the nature of the modification. We simply observe it in a larger volume. And that comes also from this simplistic picture to the fact that all the energy is done at this threshold level, and it's very hard to deliver more. To deliver more, you need to change the configuration of your, obviously the micro-explosion regime, for instance, is not the same configuration than the nanostructuring regime. So in practice, people use more tightly focused beam, for instance, for micro-explosion, to have this clamping at a higher level. But I will come back to this type of consideration in the second part on semiconductors, because it's a critical part. I mean, that's the reason why people have failed to process semiconductor for a long time.
Is it in your previous slide? So I don't understand if the optical storage of data is a stack of different layers which are raised by a laser, or if it you can control the depth of the because it is in a 3D.
Yeah, this on the left image I show a 2D plane, a two-dimensional plane. On the right, it's some results obtained by a Kazantzis group in Southampton. They use a 3D. I mean, to demonstrate this high capacity level, it's true 3D. And what they show there, for instance, is color plots. So each color corresponds to a birefringence level. It's a given information. You see, we have different planes. It's a reading at different planes inside the glass.
And we can read the informations in this 3D structure.
So they read the information optically by standard birefringence microscope. You take a birefringence microscope, you will create these images coded with these colors from which they can retrieve. So if you are interested, I mean, they have made a very impressive demonstration on this basis. Yeah, and these numbers I give, so this 32 states and 8 states, is something that was apparently the limit of the technology in terms of information you can readily retrieve after writing. We'll start the second part, where my goal will be to quickly turn to semiconductors, which is more a field of research at this point. So to reach this type of materials, first comment I'd like to make is there is an interest to broaden the spectrum of ultrafast laser processing. So to illustrate this view, my point is to comment on the fact that actually it is the same type of lasers we use for laser processing that the lasers we use in laboratories as to create secondary sources that emits extreme radiations from XUV pulses to the terahertz domain that have opened great perspectives for fundamental sciences, but these extreme radiations are still not used for laser or material processing so far. There are probably two main reasons for that. First is the complexity of these sources, but the second justification is also probably because all these extreme radiations have very modest energy. So it's very hard to directly modify your material with these extreme radiations. But we have solution to this problem. And to illustrate that, we work, for instance, of what people call seeded control strategies, which consist in not directly using the extreme radiation to modify the material, but to use this extreme radiation to pre-ionize the material. And then we can rely on the non-converted part of the light to deposit the energy in the pre-ionized material. And in that case, then we can expect to take benefit from all type of radiations. So there are different motivations to make this effort to broaden the spectrum. Obviously, going to XUV, the same way lithography has moved to XUV to reach the nanometer scale control. There could be an interest for laser processing to move in that direction. And and for the infrared part, what becomes interesting is that it can give the possibility to process extremely narrow gap materials in 3D, like very important materials like semiconductors, silicon. So having said that, we need to remain modest in the sense that it is extremely hard to make an experiment where only the wavelength will change. So most of the time, when you change the radiation, some other parameters will change. So to make fair comparison between processing performances for different wavelengths, it can be very challenging. So in practice, in our lab, for instance, we tend to limit ourselves to deep UV 257 nanometer and 5 micron. And we have worked a lot on the methodology aspects to have a reliable comparison between all these radiations. So to make sure that what we discuss is an effect of the wavelength changing drastically the nonlinearity of interaction, we rely most of the time on a single master oscillator, and we convert the light by optical parametric amplification to go for the infrared, and harmonics if we want to go to visible or deep UV. So changing the wavelength in this very large domain, obviously you will change drastically the absorption processes. And then you can revisit very basic questions like the resolution, precision, repeatability, and also efficiency. The efficiency is something in terms of processing is something very important for technology developments. So this is kind of engineering and while revisiting the physics questions. So I return to the advantages of using ultrafast light for laser processing. So it is the low thermal budget of these sources and the capacity to make subdiffraction limited resolution machining that is a key for advanced processing. So on this image, I show probably the smallest crater produced by a femtosecond laser beam. But what is very impressive there is to compare the size of the beam to the size, the precision you can achieve for machining. There are usually two argued benefits to explain this extreme precision we get. First is the concept of determinism, which consists in saying that when you move from long pulses to very short pulses, you move from a stochastic response of the material that depends on defects to a situation where you create by yourself your defects, you create the free carriers at a density so high with ultra short pulses that then you have a strictly deterministic response independent of the quality of your material. And so you can describe the response of your material by a very strict threshold, meaning that then with your Gaussian beam, if you exceed just at the center a little bit the threshold, I mean, you can arbitrarily adjust the precision of your machining. But there is another benefit that people argue to explain this high precision, which is the concept of nonlinear resolution. So it's very similar to nonlinear microscopy. The idea is to say that what matters, and that was one of the comments we got at the end of the first talk, the first hour. What matters is not the delivered profile. What matters is the absorbed profile. And so if you absorbed the intensity in the nonlinear manner, so again, if you look at the multiphoton process with n photons, it will be intensity to the power n. And you have naturally a narrowing of the absorption profile. And this is what is beneficial for microscopy, and people tend to say it's beneficial also for machining. So revisiting the question, changing the wavelength, actually, we realize that these two concepts should not be invoked, at least together. They are completely incompatible. And that's the point I will be discussing there. So again, we have done experiments where we did this ablated spots, but with very different conditions. So from deep UV to mid-infrared, and changing the band gap of the dielectric materials from 4 to 10 eV. So you see, if you look at the situation in terms of multiphoton pictures, we move from linear absorption to something extremely highly nonlinear. Typically, if you were thinking in terms of multiphoton absorption, it would be more than 15 photons involved to explain energy deposition. So of course, with this type of experiments, we are interested by the energy threshold for modification. But more interesting on that part, it was to look at the size of the produced features compared to the intensity profile. And we found that all the quarters we were measuring independently on the situation can be completely explained by a thresholding at a given contour level of the profile. I mean, as you can see there, even the defects of the beam profile can be seen there. So there is nothing, this precision has nothing to do with the nonlinear absorption of the light. And we have probably too often invoked the concept of nonlinear resolution in the domain. This tends to indicate that if you want to increase the resolution, you must fight against the optical limits, and then deep UV is very likely something we should not overlook in the domain. So as I said, the other advantage of femtosecond is not only the precision, also the capacity to work in 3D in dielectrics and polymers. And the question is, how about translating this in semiconductors and materials like silicon? If we were able to do this in silicon, if we were able to write waveguides the same way we do in glass in silicon, or to make index engineering, obviously we will be immediately relevant for silicon photonics. Silicon photonics is a rapidly emerging, growing field of technology. With the laser writing, we may have a chance to move these two-dimensional technologies to 3D, could be a booster for developments. Obviously, we can be relevant for industrial processes, but it's also interesting to notice that microfluidics is also seen as a solution to cool the most advanced chips. And so if we were able to create channels inside the chip immediately, we would be relevant in that domain. But then my point now would be to say that this is an ideal vision, but it is much more challenging to modify the bulk of silicon. So we can return to the comparison between dielectrics and semiconductors. So the main difference I will be discussing is the band gap. For dielectric, I will take a typical 10 eV band gap, while for semiconductors, we go down to 1 eV, 1.1 if I take silicon. So if you take the standard wavelength of femtosecond lasers, 800 nanometer or 1 micron, as you can see on this picture, we are immediately relying on high order multiphoton absorption processes. If we want to initiate similar processes in semiconductors, we have no choice. We have to increase the wavelength. We have to go for the transparency domain of silicon or semiconductors. So in practice, everything I'm going to show has been done between 1.3 and 2.2 micron wavelengths. That corresponds only to the 2 or 3 photon process, absorption processes. So with this, at least we can expect to have similar local energy deposition inside semiconductors. And it is a pure technological consideration. Now we have also to consider that we will have also some physical aspects that will be strongly modified moving to semiconductors, but I can also associate this to the band gap. Small band gaps means high refractive index and also increased nonlinearities. So if I take just one example, I look at the 2 photon absorption coefficient of silicon compared to silica is 2 orders of magnitude higher in silicon. So in practice, when I will focus the light, I will tend to create carriers all along the beam path, even if I target a specific zone inside the material. Something I have to consider is that I have increased the wavelength. Long wavelengths means reduced critical plasma densities. That means beams more sensitive to plasma effects, to the plasma refractive effects. So in practice, I can create more easily a plasma and my beam will be delocalized in an easy way by the plasma. So that's exactly the main reason why all attempt to focus ultrafast infrared light inside silicon have not reported permanent modification for long times. So where you can, in an experiment, you can look at this prefocal excitation in this situation can be done with luminescence measurements. If you look at the luminescence of the free carriers you create along the beam path, you see, for instance, on this experiment, a cone of light, but not much delivered at the focus. So to solve this problem, I mean, people have concentrated the efforts on the experimental and modeling parts. So again, we use a microscope objective designed for infrared light. In this case, 1.3 micron, 60 femtosecond pulses. We focus this inside silicon wafers. And we developed probe experiments to look at the excitation inside the material. And by these scanning microscopy systems, we can reconstruct the intensity we are able to deliver inside silicon, so that then we can also compare to some modeling of the nonlinear interaction, accounting for the propagation, ionization, and plasma effects, and to learn about the limits for processing silicon. So the most direct way you can look at the excitation inside silicon is to rely on infrared probe imaging microscopy. So again, 1.3 micron wavelength. So again, my point there is more to illustrate what is a probe experiment that gives you enough time resolution to observe a transient microplasma inside silicon. So in practice, we take our femtosecond laser, we split in 2 parts. One is a probe, delayed in time. You have a delay line that you can adjust so that you can illuminate the sample at different times. And while you irradiate, you focus the light inside it, and you observe this with a transmission infrared microscopy imaging system. This will give you this type of snapshots. For instance, this snapshot is done 10 picoseconds after the pump. After the pump is arriving at the focus, you have this darkening of the focal volume. That is actually free carriers that you probe by inverse Bremsstrahlung absorption. So what is nice in this type of experiments is that you can observe the microplasma, the geometry, but you can observe very interesting things. In silicon, compared to dielectrics, because of the high mobility of free carriers, you can even observe that as a function of time. So this is snapshots taken at different times at the nanosecond time scale. We see the plasma spread out inside the material. So this is carrier diffusion that is occurring inside the material. But more interesting for us was to look at the gray level on these images. The gray level gives you the free carrier density. So we can translate the transmission in terms of free carrier density, transmission level, the local transmission measured there in terms of free carrier density. And then if we change the energy of the pump, obviously when we increase the energy, we see that free carrier densities, excitation is improving, but you also observe a strong saturation at a level which is relatively far from the critical plasma density, which is a typical criterion taken by people to describe modification of a material. So this observation was totally consistent with the fact that with this type of configuration, we will never observe a permanent modification of silicon, only transient changes inside silicon. So then the next step was to demonstrate that this limitation actually comes from it's an optical limit. So for that, we did experiments and simulation looking at the intensity profile, the intensity delivered at the focus for different energy conditions. So what you can already see from the images is that when you increase the energy, you increase the volume, but the red level, the intensity delivered is not much increasing there. And by simulation, we can more or less describe this, that shows that we tend to account properly for the nonlinear processes from simulation. So with repeating measurement and simulation, then we can extract from all the profiles the delivered maximum energy density, what we call the laser fluence, as a function of energy and as a function of numerical aperture used to focus the light, up to 1.5, which is the maximum you can reasonably do with a conventional system. So the first comment you can make from all this is that, whatever the numerical aperture, we have a clamping of the intensity which is delivered inside the material. And even with the highest NA, it clamps at a level which is still far below what you will need to modify permanently the silicon. So it's a direct demonstration that this intensity clamping is what is making very difficult to achieve modification inside silicon. And in none of these experiments, we observed the permanent modification in silicon. So now this leads me to the last part of my talk, where I will review the current research to find solutions to this problem. So the first type of solution, at least the first proof of concept, was based again on this measurement, where I was showing the delivered local fluence as a function of energy for different numerical aperture. So we see that we clamp in all cases, but we also see that the plateau level is increasing with the numerical aperture. So now if we take the plateau level and we plot as a function of NA, we have these points. And if you extrapolate these points, you end to the conclusion that in principle, if you are able to make an experiment with a numerical aperture of about 3, you should be able to make a modification inside silicon. So first, it may sound unrealistic, but in practice, at that point, silicon turns to an advantage because it has a high refractive index. And then the same way we use oil immersion to achieve imaging or processing with numerical aperture up to 1.5. If we go for solid immersion focusing techniques, we can rely on numerical aperture up to 3.5 in silicon. So the simplest way you can perform a solid immersion focusing experiment is simply to replace the flat sample in a spherical sample and focus the light exactly at the center of the sphere. If you do this, you are in this situation that you totally suppressed the refraction at the air-silicon interface compared to the flat sample, simply because the curvature of your beam matches this interface. So in practice, when you are in this situation, when you cross the interface, the definition of numerical aperture again is n sine theta. In this situation, when you cross the interface, theta is not changing, but n is changing from 1 to 3.5. That means that when you do an experiment with a numerical length of numerical aperture, a given numerical aperture, you are actually doing an experiment with an effective numerical aperture multiplied by 3.5. That means that if you work, let's say, with this set of numerical aperture, this set of microscope objectives, now you can perform experiment with an effective numerical aperture from 1 to almost 3. So what got very nice at that level was that from that curve, we knew that this will not work. But as soon as we have tested this numerical aperture, we got the first success. And this is summarized on this experiment. We don't see much the modifications there by infrared microscopy. But this was the first modification observed inside silicon using a femtosecond laser pulse, 1.3 micron wavelength, but the need for this very high numerical aperture. So it was a proof of concept that there is a feasibility. Things needs to be optimized. What was very nice there was also the energy level. We used this very low level of energy because we knew from the previous treatment that working above 20 nanojoule was already at the saturation level. So it was not a matter of energy. We have tested pulse energies up to millijoule before this experiment with no success. For this particular experiment, what it was nice was to be successful with such a very low energy level. So it's very hard to see with one pulse there, but with log scale we see it. And obviously, as soon as you get a modification, you are interested by the apparent index change associated to the modification. That's the reason why we have developed an infrared phase microscope so that we can measure the local refractive index inside the silicon. And we found in this particular experiment, I want to say this particular experiment, a negative index change, which is not consistent with the fact that we do kind of amorphization, but we more likely create porosities inside the material. So that was a nice proof of concept, but obviously in a configuration that will not bring very good perspectives for technology transfer. So we looked at other solutions to this problem. So we looked at the temporal domain also. So the same way you can limit the intensity in the prefocal region by increasing the focusing. You can rely on slightly longer pulses also to decrease the power and limit the nonlinear limitations. But this is the type of observation people make if they go for the picosecond regime. So these images show the infrared lateral view of modification created with very conventional numerical aperture with 10 picosecond pulses, but with the same conditions. So you see there is something not reliable that we associate to nonlinear distortion of the pulses, and that we could also confirm by other type of experiments where we measure the damage probability as a function of pulse energy, where we interestingly found the usual response that above a given energy that defines the damage threshold, we move from 0% damage probability to 100%. But more surprisingly, we found in this experiment that if we keep increase the energy, then we can return to 0. We have a strong delocalization of the light and then return to 100%. So for us, it was clear evidence that we are still strongly limited by nonlinear propagation effects. And this delocalization make very hardly repeatable writing. So we explored different strategies. One is to rely on, I would say, an accumulation strategy, which was based on the fact that, again, the difficulty with intense single pulses is that we interact too much with the material, and that limits what you can deliver at the focus. So the idea behind this accumulation strategy was to say that if you work not with a single pulse, but with a train, ultra-fast train of less intense pulses, of course, these less intense pulses will excite less, but obviously in a more localized manner. So then the idea was to say that if the pulse can be fast and long enough, we may have a chance to accumulate carriers or heat at the focus until we observe the modification. So to design the ideal train of pulses, we need a timescale analysis. So, but that's the point where we had the point probe experiments to look at the free carrier lifetime. So typically we measure that the typical lifetime of this microplasma we create in silicon is 2 nanoseconds. And if you look at the heat, the time you need to dissipate heat from a microscale volume in silicon with simple consideration, you find also that the nanosecond time scale is relevant. So this means that if I can create a train of pulses with a repetition rate more than gigahertz, so less than 1 nanosecond between pulses, then I should be able to very efficiently accumulate heat and carriers at the focus, and obviously, and hopefully get a modification. So the way we create these ultra-fast trains of pulses is a technique we call polarization splitting technique, which consists in sending the single intense pulse inside a stack of birefringent crystals, all rotated at 45 degrees. By propagating in each crystal, actually you split the incoming radiation in two components, delayed in time, the delay driven by the thickness of the crystal, and the two indices of your birefringent crystal. So we have a properly engineered of 6 crystals. Then we have the possibility to create trains of 64 pulses, 2 to the power 6, and at a repetition rate more than terahertz, so much faster than what we need in principle based on our analysis. So first, when you do this type of experiments, you need to be sure about the conditions you apply to the material. So you need to check that you have these well-defined trains of pulses, and that can be done with autocorrelation traces. This is confirming that we can measure this train of pulses. And then we repeated all the analysis we did with these trains of pulses. So this, for instance, shows with a single intense pulse at different energies the delivered fluence. And for comparisons, this is the delivered fluence with a train of 64 pulses. So this may sound already attractive there. If you plot this delivered fluence as a function of energy, as you increase the number of pulses in the train, you see that still we observe a saturation, but we tend to saturate at higher and higher level, which may sound also very beneficial. But if you are completely honest, this is not totally correct, because this is again the delivered energy. What we should consider is the absorbed energy, not the delivered energy, because obviously when you change the temporal characteristic of the pulses, you change the absorption and you change also the threshold for modification. So if you want to make fair comparison, you need to compare the delivered fluence to the fluence threshold for modification for a given train. So that's something you can only measure on the surface. And when you look at the ratio now, you see we have an improvement, but it becomes much more modest. Typically, the physics behind this is not fully explained, but we found that there is an optimum of pulses to put in the train, typically 8 to 16 pulses. And we could improve the condition by typically 60%, which is significant. And that could be confirmed by some laser writing experiments. So I'm sorry, it's not very visible there, but what I show at the top is infrared top views of irradiated spots for different conditions. So 1 pulse, 8 pulses, 64 pulses. So what you should see there is that there is nothing. So whatever the number of pulses we put in the train, if we still work with 200 femtosecond pulses, you will never find a permanent modification. So to observe the benefit of the accumulation strategy, we move to 5 picoseconds. 5 picoseconds is still too short to obtain a modification in silicon with a single shot, as it is shown there. But as soon as you start to split the same amount of energy in 2 pulses, you start to get a modification, but not very reproducible. And if you split again the same amount of energy in more pulses, 4 in that case, then you can stabilize the writing process and you immediately observe the benefit of this pulse train strategy. If you move to 6.7 picosecond pulses, 1 pulse is enough. I mean, it is long enough to create modification. But what we observe is that by increasing by splitting the energy in more pulses, we can make features that are better controlled somehow. And we have the symmetricity coming from the polarization splitting, which is an interesting aspect. So something beneficial, but that will not totally solve the problem of ultrafast laser writing in silicon. but still capitalizing on the knowledge that actually we need high angular component and relatively long pulses to modify. We start to revisit experiments that people were doing in dielectrics so far. So for instance, there is a large matter of applications with the use of what people call Bessel beams, which are non-diffractive beams that allows to make high aspect ratio structures inside materials. So the idea is that you can maintain the spot size over very long distances and directly write channels inside the materials. For the case of silicon, what we needed Bessel beams created with very high angles. So we had to develop what we call an Axicon lens doublet, a new approach based on Axicon lens doublet, very simplified. But we confirm that by this simple method, we can produce spots smaller than the equivalent Gaussian beam. And also, this is a Gaussian spot along the propagation direction. And this is how it looks if you work with an appropriate Axicon lens doublet. And so we applied these beams to try to tentatively machine silicon in that case. So this is a side infrared view of a silicon wafer irradiated with different number of pulses with these configurations. And so what you see there is that as you increase the number of pulses, progressively we can propagate a modification inside the material up to a through modification over 1 millimeter. So in practice, this means if you look at diameter compared to depth, the ratio is typically 700 in that experiment. And interestingly, for that experiment, we found that the refractive index is positive. So that gives directly the vision that it is possible to make vertical optical connection inside the silicon chip, which could be an interesting application. So as we have seen in previous slide, in this type of experiment, we have the possibility to observe the microplasma we create inside the silicon. So now if we do the same experiment, but not using a picosecond laser, but a femtosecond laser, we know that we will never create a permanent modification, but we can create a well-contrasted plasma inside the material. So with these probe experiments, what we observe is actually that we observe a plasma front that propagates inside the material at the speed of light, as the light is delivered along the optical axis. Again, with the same special characteristics, but this is a channel of free carriers. This is a conductive transient materials. So we can create this plasma string in 7 picoseconds. We know that the typical lifetime is nanoseconds. So this gives, for instance, the vision of electrical vertical connection inside silicon chips that could be optically controllable at gigahertz repetition rate. So for the last part of my presentation, I will be describing probably what is today the best level of control we can achieve in this type of experiments. So this is based on a previous study, which was to look at the dependence of the material response to the temporal contrast of the pulses. So the point there is to realize that depending on the laser technologies you use in practice, in time, you don't get necessarily a very well-defined Gaussian beam. But because of technology limitations, you always find a kind of pedestal that defines a temporal contrast in your pulse. So looking at the potential dependence to this problem, actually, we developed this type of experiments where we do not want to manipulate. It's very hard to manipulate the field, the temporal envelope of a beam. The way we simulate a different contrast level was to combine different pulse durations. So this is an experiment where we have two paths. One can be stretched, the other can be directly sent to the sample. So then we have femtosecond laser pulses potential pulses that can be stretched more than in the picosecond domain, and then that we can synchronize electronically with nanosecond pulses. So just by combining these different components, we can mimic any contrast imperfection. And just to give you an example, this is the typical temporal profile you will find for fiber laser technology. So you see you have a kind of picosecond pedestal that we were mimicking relatively well just by combining a femto and picosecond pulse. So what was very surprising for us at that level was that to realize that we have a problem which is strongly dependent on the optical contrast. In the sense that when you try to make modification, okay, again, it is top view infrared microscopy images of irradiated spots. As soon as you start to play with the contrast of the irradiation, you can observe permanent modifications that are completely inaccessible by a pure femtosecond pulse. So it's like an imperfect contrast can lead to modifications that was impossible with initially well-contrasted pulses. So this was actually a very critical point to understand the literature on that subject. I will come to this in a minute. But we did a full analysis. So degraded the picosecond contrast by adding a picosecond pre-pulse, a picosecond post-pulse. And we found the most favorable conditions actually for contrast levels that was corresponding relatively well to the typical contrast for fiber laser technologies. But also interesting to note that for the nanosecond contrast, actually we were able to predict the modification just by accounting the background, the nanosecond background. So this experiment was a demonstration that some studies were reporting modification inside silicon with femtosecond laser pulses, but it had this actually in practice, these experiments had nothing to do with the femtosecond pulses. Everything was coming from the background of the laser technologies. This became very clear when we started to try to sort the literature results, depending on the groups, in terms of requirement of the NA requirement and pulse energy requirement to observe modification. Once we have sorted all the results based on the different laser technologies that were used, actually everything got logical that higher is the contrast, more challenging is to achieve modification in silicon. And it's a very important aspect that people should consider to develop the applications. This is also the type of knowledge that allows to improve the writing process. So now to achieve the highest level of controllability, we turn to a kind of plasma optics concept in a sense that we do not only rely on sufficiently long pulses like picosecond pulses, we now exploit the femtosecond lasers to create a pre-plasma favorable for the picosecond laser writing. So in practice, we observe that with an appropriate femtosecond laser pulse, we can create microplasma condition dense enough so that actually the writing pulse deposit its energy on the plasma front. So this is visible on this experiment. Again, the femtosecond laser pulse by itself is not creating any modification. The picosecond by itself can create modification, but when you start to combine them in an appropriate manner, you see that the threshold for modification decreases, but also the spot, the damage modification is also drastically decreasing. It's clearly there where we plot the volume of the modification, changing the energy of the two pulses, and then you see that we have a kind of valley there for a specific set of parameters that allows to make extremely small modification. We have associated these favorable conditions to near critical plasma densities. So again, with the POM probe, we have found that actually with these 0.85 NA objectives, we are creating a free carrier density that makes that actually the plasma front is extremely dense And typically the light cannot propagate more than 1 micron inside this plasma. And so all the energy is deposited on this front. So in terms of resolution performance, what is interesting is the lateral resolution. So this is the comparison of the modification size without the plasma and with the pre-plasma. So you see we can significantly decrease the lateral size down to the diffraction limit. And more spectacular is on the longitudinal resolution. Without the plasma, we are limiting there, so we have something elongated. But with the plasma, we have almost the same resolution longitudinally and laterally. So this is visually how it compares. This is the best writing conditions, top view, lateral view. And now with the critical plasma seed approach, the almost 1 by 1 by 1 micrometer voxels that we can produce. When you start to make more complex 3D patterns inside the silicon wafer, this image, we don't see the scale. So the basis of this Eiffel Tower is 70 micron. So this gives you a bit the level of control we can achieve. So from top view, dark field top view, this is a 3D Eiffel Tower, and you see that we can reasonably now work at the micrometer scale. If we return to the first part of my presentation, I was talking about spherical aberration. As you see there, we write at different depth. So we have the problem of spherical aberration in silicon is extremely important. And so when you do this type of processes, you need to, for each layer, for each level, you need to correct appropriately the spherical aberration. This is just a technical comment. So now to demonstrate that everything was coming from the critical plasma front in our experiments, we turned back to simulations. So again, we have the possibility to calculate the delivered laser fields without and with the plasma front. So first we see that light is not propagating very far after the front there, but it does not describe energy deposition. What translates the energy deposition most of the time is more the plasma density. This is the absorption of light that is increasing the plasma density. But what you see there is that, okay, there is a change, but not a strong confinement of the energy deposition there. To describe the confinement of energy deposition, we had to clearly calculate the deposited energy and not only the plasma excitation. So that means that the picosecond laser is not only ionizing more the material, it is also heating the plasma. And this part of energy is the main part leading to the modification. So the plasma heating occurs just on front of the plasma, causing the modification. And this observation was corresponding relatively well with these bright spots that we could directly observe as soon as we get a modification for these conditions. So to definitely conclude that this is a plasma front that gives a driving role in these experiments. Actually, we realize that this plasma that we create, I mean, this is a geometrical focus, is mostly in the prefocal region. So if we send the picosecond writing beam a little bit on front in space, we should have a better process. So that's what we did, changing the divergence of one beam compared to the other. We moved the picosecond beam so that it interacts more, it focuses more efficiently on this front. And we observed a decrease of the threshold for modification by 70%, which was consistent with this idea. And we did the same thing laterally, making relative move of the two beams. What you observe is that when you move the femto in the pico, the modification moves. But when you move the pico, keeping the femto fixed, the modification remains fixed. So everything is driven by the femtosecond pre-pulse in these experiments. This is clear from this. And things get also interesting when you start to make relative move in time of the two pulses. So what you see on this is modification for different delays between the pulses. So when the picosecond arrives first, so above 0 there, we have the picosecond writing resolution. But when delay becomes negative, It means that picosecond arrives after. We have the femto-pico resolution that we observed before. Now, if you go for very short delays, so that the two pulses overlap, something intriguing there is that we have missing spots. It's like the femto, if it is sent at an appropriate time during the pico, it inhibits the effect of the pico. And that's something we can also quite simply understand in the fact that when you send the femto inside the pico, the first part of the pico will interact in the usual volume, the usual pico volume. But as soon as you create the plasma with the femto, the rest of the interaction will be done on the plasma front. But not all the pico will interact in the plasma front. So in practice, you are dealing with an experiment where the net energy density is decreasing because you are doing two interactions with one pulse. So observables that were very consistent with the fact that the plasma front has a leading role in these experiments. The point that was also very interesting in this experiment is that not only the spatial aspect is improving, also the controllability of the modifications is increasing by this concept. So this is illustrated there, for instance, where you see the modifications. I know, I'm sorry, it's very hard to see. Changing the writing, the number of pulses for writing. So first observation is that the size is not changing much. So it is more or less contrasted, but the size is not changing much. This is very difficult to do with a single pulse. Most of the time when you increase the number of pulses, the modification is growing. So this is the first benefit of the approach. But then we observe also that, okay, with one pulse, it's almost invisible by standard microscopy. The way we can reveal that we create defect with only one pulse is by microscopy scattering or dark field microscopy schemes. So this is a spot we can reveal by scattering approaches for the first pulse. So looking at the scattering intensity as a function of number of pulses for writing, we found a linear trend that tends to show that we accumulate shot after shot low density defects. So that creates more and more signal in these experiments. So then the question is, what are the type of defects we create in silicon? We know that femtosecond lasers can make G or W centers, but we don't know in these particular experiments what the type of defects we create. But interestingly, we found also that when you increase the number of defects, you observe also that you build an anisotropy in the defects. So looking at the strongest modification we could produce and scanning the beam on very large volume, we tentatively did some TM analysis to learn about the modification. And for the first time, we found some amorphous domain in this experiment. So there is nanometric domains inside silicon oriented by the electric field of the laser and somehow exhibiting a kind of periodicity that could allow some analogy with some work done in dielectrics, but we are just at the beginning of this material response. So since we modify silicon by defect formation, actually, we can also relax these defects. So just by thermal treatment, we can erase these defects inside silicon. So where we can do it in the experiment is that after writing with femtopico, we can apply a nanosecond laser pulse to hit locally and erase the spot we have previously produced. So in this experiment, we show that by combining the two irradiation approaches, we were able to cycle and write and erase the structures inside silicon more than 100 times. That gives immediately application perspectives. To illustrate that, we did, for instance, this QR codes written at a given depth inside a wafer, given QR code, erased, and rewriting with a different information that was successful a few times at least. To illustrate also the vision we have for this, we wrote some Fresnel lenses exhibiting a given focusing power, then erased, and we rewrote at the same place a lens with a different focusing power. And finally, because we rely on defect accumulation, we can relatively finely adjust the phase of the index change. So we can make clear index engineering in this situation just by adjusting the writing beam or the raising beam. So this is different phase level we can access. And from this, we did some phase plates to manipulate the beam characteristics, at least showing that there is a feasibility to engineer micro-optics component on this basis. So this is my last slide to conclude. I have reviewed three-dimensional laser writing applications. I hope that the last part I've shown that it becomes progressively applicable to semiconductors, even if it is relatively recent and it has been challenging. The next steps on this type of activities is to learn probably more about the material changes that are accessible. So this will be probably an activity on which there will be effort in the field. We should look for improved controllability, of course, depending on application. Not sure how far we will go in terms of control. Is it realistic to think that a laser will have at some point an atomistic control in the bulk? It's an open question, but that people explore is eventually for quantum technologies. And one comment I'd like to make, at least for semiconductors, everything I have shown is just above the modification threshold. In dielectrics, I have been talking about extreme conditions, microexplosion. This has not been reached yet in semiconductors because it was very hard to increase the energy density to cross the threshold for modification. So this is probably also an aspect on which people will concentrate their efforts. And obviously it will rely on new methods, but progressively we see mid-infrared lasers more and more applied to address these questions. So to finish, I will simply acknowledge all the people that have been contributing, at least for the research I've been showing on the last part of my presentation. Thank you for your attention. And if you have questions, I'll be happy to answer.
Thank you for the great talk. So I'm sorry, I might be confusing things, so help me out, please. So your conclusion was that ablation, well, we never went above the ablation threshold, damage threshold in silicon yet, but Disco, and you have shown a picture of them, has been selling machine that can do wave dicing for around 10 years now. So is there something that I'm not understanding here?
Okay. So I confirm that an infrared femtosecond laser with a very clean pulse will never produce a modification in the bulk of silicon. So that's I confirm this point. When you say there is many applications, it's completely true that semiconductors are widely processed by lasers, but these are surface experiments. So when you talk about dicing by ablation, it starts from the surface.
Okay.
And so, yeah, in terms of controllability and processes you can envision, so everything I have been showing is pure 3D in a sense that everything I have shown does not depend on the depth. I can achieve the same thing, whatever the depth in the bulk.
Okay, because this is clearly not what they are selling or marketing or even patenting actually, but okay. Thank you.
Thank you, David, for this huge amount of results and nice results. One small question about the repeatability, which is always a challenging aspect when using lasers, as we are doing. You've shown us, oh, sorry. You've shown us results with burst. In the case of a duration of 5 picoseconds, maybe Cécile will help you, I don't know. When you presented results with the burst,
Yes, yes.
I don't know the number of the slide, by increasing the duration of the pulse at 5, yes, exactly, 5 picoseconds, and with the 2 pulses here, you observe no repeatability that might appear, but do you have any idea of why? And how can we little bit more maybe challenge the repeatability of ultrafast laser processes that might interest our community as well?
So most of the time we associate these limitations in repeatability to the limitations everyone will face, whatever the type of processing you do. So maybe we can return up to this. So this is, I'm sorry. So if you plot the probability, damage probability as a function of incoming energy, you never obtain a perfectly sharp transition from 0% to 100%. It's progressive. So there is different factors that can contribute to this slope, which is more or less pronounced. But we are particularly facing these difficulties for semiconductors because we hardly exceed the threshold for modification. So even if we increase the energy, it's like actually, I should not plot the incoming energy there, but I should put the delivered energy. And if I do this, even if I increase my laser energy, I hardly go out this transition region. So, okay, there is different contributions that could come from this transition, the stability of your laser. But we found actually for surface machining that, this is the only contribution if you work under the picosecond regime for ablation. Of course, if you work with longer pulses, it can depend on the number of defects you will find in the samples. So that's what people study, in particular in the nanosecond regime. So there are different factors that can contribute to this, but there is always a transition, and we are particularly sensitive to this because on that curve, basically, it's already very hard to reach this point. So the best we can is is most of the time close to this transition. We have been sitting below this transition for a long time. We have been hardly exceeding this threshold. And now the next step is to push a little bit more. And so the way we interpret this, again, it's exactly the same energy which is applied on the sample for all these cases. The only thing we understand is that we exceed sufficiently the threshold for modification in this case to make it stable.
So finally, the big deal is that it's even more difficult for silicon processing.
Yeah, at least for the bulk, yeah.
The bulk. Thank you.
What is the next semiconductor that you are going to investigate?
Sorry, the next?
What is the next semiconductor that you are going to investigate when you are done with silicon?
Good question. I mean, we have been concentrating for a long time on silicon, which has been very challenging. So to be honest, we even try to decrease a bit to work with semiconductors exhibiting a bit larger band gaps because we had these difficulties. So I confirm investigating different semiconductors, smaller is the band gap, more challenging is the situation. So we did so nothing exotic there, but we did already some experiments in germanium. pushing a little bit further in the infrared, the radiations. We have demonstrated some feasibility, but again, even more challenging than silicon.